In this lecture, we're trying to find the inverse of a matrix in terms of an infinite sum. Okay. So we have seen there are multiple ways of computing an inverse. So this is one of them. So here we're trying to extend this idea from normal sequences, if from real numbers, if x belongs to R or C, and if modulus of x is less than 1, then 1 minus x inverse can be expressed as 1 plus x squared plus etc. to infinity. This is one way. Similarly, from extending this idea, we can actually express 1 minus a, the whole inverse, as I minus a, the whole inverse, if A is a matrix, plus I identity matrix plus a squared plus etc. If norm of A is less than 1, or another way to say is spectral radius of A is less than 1. Okay. So this is something which we're trying to do, but we have to systematically prove this, that this can be used to find the inverse of A. Okay. So the corollary which we're going to look at is, let me change the color. Corollary is that A be a square matrix and A is invertible if there is a matrix norm given by this 3-bar function such that norm of I minus A is less than 1. If this condition is satisfied, then A inverse can be expressed as k is equal to 0 to infinity I minus A all raised to k. So A inverse can be expressed as the infinite sum of I minus A, where k is varying from the powers of I minus A raised to k, where k varies from 0 to infinity. So let's try to prove this. So we're given norm of I minus A is less than 1, which implies series k is equal to 0 to infinity I minus A raised to k converges to some matrix C, right? To some C, where C is, okay, let's not confuse this with complex. Some C where C is n cross n. Okay, so we've seen that entries of I minus A raised to k is upper bounded by rho of I minus A plus epsilon whole raised to k. We've already seen this. This is the previous result, which we've proved in the previous lecture. Okay, so each element of A of ik will be, let's write this like this, phi j. Every element of this, fine. This is rho of less than this, right? Which implies every entry. So this is the ikth term, right? So ikth term is actually upper bounded by some value, and rho of ij is actually less than 1, right? So this will be value will be also less than 1. So we can say that this every entry is less than some arbitrary constant C, less than let's some constant K, right? Every element. So if I just add up these matrices, right? Every entry is convergent. Okay, let me write this. Every entry of okay, the kth matrix is convergent. So if you sum such AK matrices till infinity, I minus AK to K is convergent. Why is this convergent? As K approaches infinity, this matrix will tend to zero. But even before approaching infinity, all the values are bounded. We already know that, right? This is convergent. So let's write A into sigma K is equal to 0 to n I minus K. This is some arbitrary K, n which we are taking here. We have to prove that this is the inverse, right? This actually is convergent. So there's no harm in multiplying this, right? So here we will be taking this sum and finally put K is equal to infinite. So this is A times sigma. If you can prove that this is equal to identity, then we can say that this is the inverse, right? Fine. That's the idea. So A can be expressed as, we have to check where this is the identity. So A into sigma K is equal to 0 to n, I minus A raised to K. A can be expressed as I minus A, right? Sigma A is equal to 0 to infinity. So equal to 0 to n, I minus A raised to K. So this is a summation which we have is multiplied by this. This is I minus A. So with I you have sigma. It's I times K is equal to 0 to n I minus A raised to K minus here we have I minus A raised to K. A plus 1, right? I think there's no harm so far. Yeah. But since we have this minus sign, okay. This is some matrix. So this is identity times some matrix. We can actually put this as K is equal to 0 to n I minus A raised to K minus this has K plus 1 terms, right? Yeah, I think this is correct. It will have one more term. There's some mistake which I'm doing. Ultimately, this should be is equal to what am I doing? I sigma k is equal to -1. Okay, let's not. Uh, let's try to simplify this. I think there's some mistake 3 times. Yeah, let's keep this here. This is a, and this one I'm trying to expand this as I minus a raised to 0. What is the definition of a raised to 0? I know. I'm hoping that this is identity matrix. Whatever. I plus I minus a plus. There's no standard definition of a raised to k. Yes, I minus k. This is I minus a raised to 2 plus etc. plus I minus a raised to n. I hope there is no doubt in this so far. This is same as a. A is I into I minus a into I plus I minus a plus etc. plus I minus a whole raised to n. Right? If I take the product of first two matrices, this is I plus I minus a plus etc. plus I minus a raised to n minus I minus a plus I minus a squared plus etc. plus I minus a raised to n plus 1. Yeah, got it. So here, if you take the minus, all these terms will cancel except the first term and the last term. So this is I minus a all raised to n plus 1, which is in fact, okay, this is for n as n tends to infinity, I minus n plus 1 tend to 0 because this is convergent. So this term will tend to 0. So we can say a into sigma k is equal to 0 to infinity I minus a all raised to k is equal to I, which implies a inverse is equal to sigma k is equal to 0 to infinity I minus a all raised to k. Okay, hence true. So this we can prove that we can express a inverse as an infinite sum of I minus a whole raised to k. Right. Let's conclude the discussion here.